Today we have Chung-En, a PhD from University of California, San Diego, who will talk about concept bottleneck large language models. Please, Chung-En, take it away.
Yeah, very thank you for having me here. Yes, and sorry about last time I got kicked offline. Yeah, and this time I will not share the full screen, so I will know if I got offline. Yeah, very sorry for that. Yeah, so let me introduce me again. So I'm Chung-En from UCSD Trustworthy Machine Learning Lab, a third-year PhD student, advised by Professor Lily Wen. Okay, so I will quickly give an overview of what my research is going on, and then thoroughly go to today's topic. So my research is mainly focusing trustworthy machine learning, and it's mainly spanned three aspects: interpretability, reliability, and safety. So in terms of interpretability, I mainly try to interpret the component in the large language model, like the new MLP neurons or the attention head. And based on this understanding, I try to control the model behavior. And then there are several works. For the reliability, I study the confidence calibration and also the faithfulness of the reasoning, control the model behavior. And for the safety part, I have studied adversarial robustness setting, including attack and defense, and also the large language model jailbreak attack setting. Okay, so these are my published works, and today I will focus on the concept bottleneck large language model. This project is for building intrinsically interpretable large language model. And I also have some other works, like the large language model jailbreak attack, and also improving the reasoning through weight editing. Yeah, and I also have some newer unpublished works, and they are also similar doing in a trustworthy machine learning setting. Okay, so let me introduce this work, concept bottleneck large language model. This work is selected by ICLR 2025. Okay, so this will be today's outline. I will first give a motivation introduction, and then briefly introduce what is concept bottleneck model, and introduce several previous work in the language model domain. And then I will introduce the method and evaluation based on the two settings we have done, the text classification and the text generation. And finally, I will give some use case of our concept bottleneck large language model. Yeah, so this will be today's outline. Method and evaluation. Okay, so let me first give an introduction. Like today we have so many closed source and open source large language model. And we use them to do a lot of different tasks, like help us doing the writing and communication. Like we also use them to help us write a paper, and also some daily coding. Like there are many coding assistants, like Cursor, Compiler, and Cloud Code. And the large language model is also some of the model are multi-module, and they are also possible to create a high-resolution image or video. Like recently, there's a ChatGPT image 2, and it's very powerful in creating the figures that also have some text, and the text is very high resolution. And most importantly, I think the most widely application is the large language model agent that it help us to do some personal decision, like maybe making a travel planning and also like shopping recommendations. Yeah, but there are some fundamental issues that even for nowadays still unsolved. Like the hallucination problem, where the model can give some answers that look promising, but it's actually not correct. So here's an example, like if you ask how many M's in the weather, then it will not answer it correctly. But for nowadays, larger model, it probably will answer it correctly. Like the model is improving. Yeah, but the hallucination problem is still persists. It now becomes a deeper end, how to discover that there's a hallucination there. But like if you are using like the coding agents, in many times it can still like generate some wrong reference or wrong citations if you are writing a paper. Or in the coding, you can still have some hallucinations, like it can do some things that you does not expect. And there are also some other issues. Like here is a classic example of the jailbreak attack. Like we input a harmful query, and then we append some something nonsense after the harmful query, which is a red part. And if you input this whole sentence to ChatGPT, then it can edit the harmful content that the model should not answer. So this red part is completely nonsense for human, but it actually can break the larger model, and we know very few about this. So why this happened?
You got disconnected. We can't hear you.
You're back. Wait. Chung-En, you're muted.
I think you're muted.
Can you unmute yourself? Okay.
Is it good now?
Yeah.
Yeah, now we can hear you.
Sorry, I'm not. I don't know why
That's
it happened. Yeah, let me continue. Yeah, so we are talking about a jailbreak attack, and we know very few about why this failure mode happened. Yeah, so that's why we want to study interpretability. So it can reveal how the model thinks by inspecting the model components like a neuron or attention head. And based on this finding, we can try to debug and get more control about model behavior. Okay, so let me introduce the two paradigms of the interpretability, which is post-hoc interpretability and intrinsic interpretability. So when we talk about post-hoc interpretability, it means that we assume any black box model, and we use some interpretability tools to try to look into and explain how the model is doing. And for intrinsic interpretability, we want to build some special architectural design to make the model that is already interpretable to most of the users. So let me first talk about what is the limitation of the post-hoc interpretability. So because nowadays we have very deep networks, this is like a ResNet, like it's already very complicated. But for nowadays, a larger model is even have more parameters and more complicated. So when we apply the interpretability tools, it's actually hard to decide which part we should focus on. There are just too many components in the model. And another problem is called the superposition problem, or the polysymmetric of the neuron. Like if we try to inspect just a single neuron and try to see what's the information encoded in that neuron, usually we will get something looks like this. Like the x-axis is the activation, and the y-axis is the different concept cumulative percentage. And we can see that in different activation regions, this neuron encode very different concepts. So this means that the information encoded in neuron is not linear. It's very nonlinear, and it can at the same time it can represent many different unrelated concepts. So this makes the post-hoc interpretability very hard to do here, because there are too many things encoded in the same neuron. So let me give a summary of the post-hoc interpretability and intrinsic interpretability. So the problem for post-hoc interpretability is difficult to scale to larger models, like nowadays large language model. And the neurons in a model or attention head, these components are often polysymmetric. Like they encode many different information, make it very hard to explain. So for the goal for intrinsic interpretability is we want to build an interpretable model that enable scale to larger models. And also we want at least some of the component in the model that they only encode some simple features that's easier to understand. Okay, so let me now introduce what is concept bottleneck model first, and then briefly go over some previous work that apply the concept bottleneck model in the language domain. So let me first introduce what is concept bottleneck model. So when we talk about concept bottleneck model, it means that there is an information bottleneck in the maybe middle layers of the model. So there is an interpretable layer, and each neuron will encode only one concept, and we call this the concept bottleneck there. So this is an information bottleneck because only the assigned concept can pass through this layer. All the other information will blocked. And after this interpretable layers, usually there is a linear prediction layers that do a linear combination of this concept and make the final prediction. So we can see that the final prediction is always a linear combination of the concepts, and this is usually more interpretable. And there are many different CBN works for image domain, like there are many previous works. But in the language domain, there's only very few works. So in the language domain, all the previous work, they are focusing on the text classification, which they use a BERT model, then try to build a concept bottleneck model using BERT to do the interpretable text classification. So I will go over these two works briefly. Yeah, but in a more modern setting, the auto-regressive larger model setting, there's no works building interpretable larger model. Okay, so now let me briefly go over the interpretable model, the CBN in a text classification case. So the first work will be the text bottleneck model. So what they do is simple, like they query another large language model like ChatGPT to generate a set of concepts and then label the concept with -1, 0, or 1 for each test classification example. So all these concepts and score are derived from ChatGPT. So after they identify these concepts and their corresponding score, they will train a linear layer to predict the final sentiment. Like in this case, it's predict the restaurant review is negative or positive based on all these given concept and score. So the strength of this work is we now have interpretable prediction because it breaks down to many different concepts, and each concept has its corresponding score. So we can directly see how the model makes prediction. We also can look into the final layer weight to see the importance of different concepts. Yeah, but the problem is, as you can see there, we need to query ChatGPT a lot of times in this framework. Like we need to query ChatGPT every time for each concept and also each concept labels. So it's hard to scale to a large data set because each example you need to query a lot of times. And there is an accuracy gap compared to the black box language model. So the easiest way will be you simply train another classifier. Usually it will perform much better. Another work is called C3M. Yeah, it's a concept augmentation with the concept label mix-up. So the main idea of their work is more like the traditional CBM setting, where they indeed train a concept bottleneck there. So in this layer, each neuron corresponds to one concept. So the concept here is now neurons, not only the text generated from ChatGPT. And
okay, I don't know why this keeps happening, but you're back.
Yeah, I'm not like look like I got offline like.
It's okay.
Article like.
As long as we can fix it, it's okay.
Okay, I'm not sure if this is randomly or it will happen like periodically. But let me continue. Okay, so we are talking about C3M. So it is indeed a concept bottleneck model structure. So now it can provide robots and interpretable text classifier. But the problem is still there. So because they need to train their concept bottleneck there, and so we need to have a lot of concept labels, and all the concept label is generated by ChatGPT. So this is still very expensive. And the same problem is there's still an accuracy gap compared to the black box language model. So let me give a summary of the current limitations. So in the current field, the CBN applied to the language domain, they have best scalability. So they rely on human or ChatGPT to like label the concept. So which is very expensive. And also we have low performance. Like in the text classification, the accuracy is usually there's 5 to 10% drops compared to the black box model. And most importantly is classification only, so it does not scale to the other use case, like it cannot do large language model, and there's no checkbox setting. And so we propose a concept bottleneck large language model to solve all the above issue. So in this work, we have two settings: the classification setting, same as the previous work, and also the new text generation setting. And they are both with interpretable layers. So for text classification, we we make it more efficient, more scalable, and it provides faithful explanations. And for a text generation, it will be the first interpretable auto-recursive library model, or chatbot. And it enables controllable generation and explainable token prediction. Okay, so let me first introduce the text classification part of our CB-LLM. So this is the whole framework of CB-LLM for text classification. Like we have many steps here, and I will go through them in details. So similarly, we first need to generate a set of concepts that is related to our classification test. So here, we also use ChatGPT, but the difference is to generate the whole concept set, we only need one query to ChatGPT. Because we are not using ChatGPT to doing the concept labeling, we just ask it to generate what's the possible concept that will be used in this test. So we only need to query it one time. And ChatGPT will give us a list of concepts that might be useful in this classification test. And then after we have a set of concepts, the main different part is we use a different model to do the concept labeling. Like we don't use human. We also don't use ChatGPT. We use a sentence embedding model to do the concept labeling. So the role of this sentence embedding model is to calculate the causal similarity between each concept and each training example. Like here, we have the Yelp dataset, and this training example is talking about the customer service is bad. So in this case, the concept 3, the unprofessional service, will have very high similarity with this training example. So like we can see that they have high similarity. So which means that our concept labels will also have high value, which means that this concept is present in a sentence. And this is done by using a very lightweight sentence embedding model, which is much smaller than a ChatGPT. And another thing is assume we have n concept and n training example. In our framework, we only need to have n plus n inference on a very small model. But like in all the previous work, you need to have n times n inference on the closed source ChatGPT. So our labeling step is much more efficient. And after we get a set of concept label, we do another step to make the labels better. So this concept correction step is fully automated. Like we don't need human to do the label correction, and it is by just doing a very simple filtering. Like we can see that, like in this example, the training example is complaining about the customer service, so it's a negative example. But the concept case here, it is a positive example that is reliable cleaning. So if the concept and the training example there belongs to different class, like we already know, because when we generate a concept, we know it is negative or positive. And based on the training data, we also have the label. So we already know if they are in the same class or not. So in the case that if they are not in the same class, then the similarity ideally should be 0. But the model can sometimes output still like give some certain value of the similarity. So in this case, we will manually set it to 0. And we observe that after we do this post processing, like there's a 3 to 4% accuracy gain. by just simply doing this double check. Okay, so after we get the concept labels, and we also clean up the label, then instead for we are ready to learn a concept bottleneck layer based on our concept label. So given a training example, it will input to a pre-trained language model, which we use a BERT here. And after this pre-trained BERT model, we will add an additional concept bottleneck layer that learn the similar pattern as the concept labels. So we require the neuron activations to have the same activation pattern as this concept label for every training example. So after this, then each neuron will learn the assigned concept, because now each neuron is activated similarly as our predefined concept score. And after we train the concept bottleneck layer, then we will later fix the concept bottleneck layers and train another final linear layer to predict the final classification. And there is a ReLU between the final linear layer and the concept bottleneck layer. This is for just filtering out all the negative activation. And because sometimes the negation of a concept is ambiguous. For some concept, it can have negation. There will be means it can mean in an opposite way. But for some concept, it's hard to define what is the negation of a concept. So to prevent these kind of cases, then we will just remove all the negative activation through a ReLU. Okay, so this is the whole pipeline of training the concept bottleneck models in the test classification case. So then now we introduce the evaluation of the CB-LLM in the classification case. The first thing we care about is performance, right? So we want to make sure that it has similar test classification performance as the black box model. And as you can see that our model have very close accuracy compared to the Roberta fine-tuned model. While the light grade part is the previous works, they have some accuracy degradation. And the second evaluation is
Welcome back.
Yeah, the second evaluation is training efficiency, where we show that our CB-LLM have a very short training time compared to the previous baseline. And the most important part is the explanation quality. That here we design two metrics to evaluate the explanation of our CB-LLM. So the first evaluation, it asks, does the concept neuron truly represent the assigned concept? That is, we want to make sure each neuron learn the corresponding concept correctly. And the second evaluation is, does the model provide a good explanation for its prediction? Like, because we have a lot of concept neurons, and for each examples, we want to evaluate, can we extract the meaningful explanation within these examples? And these two evaluations are all done through the large-scale human evaluation. That we have a lot of humans look into these explanations. And the first thing we found that the neuron in the CB-LLM is more interpretable compared to the previous work. And also, human prefer more about the CB-LLMs explanation compared to the previous baseline. Okay, then now let me introduce the test generation part. So this part is a new design that previously there's no work scaling CBN to the autoregressive generation case. So in this case, we have a more special design which incorporate two module, the CB-LLM training and the adversarial training. So for the module one, it is a standard concept bottleneck model training. So in this case, we also have a concept bottleneck there in the model. So this part is the same as the classification case. Yeah, but the final linear layer will be replaced by the large ranking model head because this is for next token prediction. So now it's still similar to classification, but we are predicting the next token. And the different part is we now have another layer called the unsupervised layer, which also feed is embedding to the large ranking model head. So we added this layer because the concept in the concept bottleneck mod layers, it is not enough to do the text generation. Because in text generation, we need to have enough information to generate a full sentence. And usually our concept set cannot capture everything that is required in a sentence. So in this case, we will add some neurons that the model have freedom to choose what is encoded in these neurons to help the generation. Okay, so now we have an unsupervised layer in parallel with the concept bottleneck layer. So we have two layers here, and the concept bottleneck layer is interpretable, and the unsupervised layer is not interpretable. Yeah, but now there is an issue called the neuron gain concept one-to-one mapping, because ideally, to achieve the full interpretability, we want the concept bottleneck model, each neuron only encode one concept, and one concept only encoded by one neuron. So this is an important one-to-one mapping between neurons and concept. And let's see what happens if this one-to-one mapping is broken. So if one neuron encodes multiple concepts, it means that changing that neuron activation, it will shift multiple concepts at the same time. So which means that if we try to control a model behavior when we change the activation of the neurons, then the model can simultaneously shift a lot of behavior in the model. And this is not a problem because the concept bottleneck layer by design, one neuron can only encode one concept. This is forced by the training. So this property is still good. But now the problem is in another direction. If one concept spread across multiple neurons, which means that one concept there are multiple neurons that can in charge of the same concept. And in this case, if we just change the activation of one of the neuron, then it will have a little effect on the model's output because there are still many different neurons in charge of the same concept. So this also makes us very hard to control the model behavior. And now this problem reappears because we add an unsupervised layer. We don't know what is encoded in this neuron, which means that the model can ignore the concept bottleneck layers and just encode every information in the unsupervised layer to make the prediction. So if the model chooses to do so, then our concept bottleneck layers will have no effect on the model's output. So now the goal is we want to remove any concept that is already encoded in the concept bottleneck layers from the unsupervised layer. So which means that in the unsupervised layer, it should not encode the same concept that we already predefined. So that's why we design another module, which is the adversarial training. So here we use the adversarial objective to remove all the concept information that we encode in the CB-LLM in the unsupervised layer. So let me explain how we do this. So there are two objectives and they are adversarial against each other. And the first objective is for the unsupervised layer, we want it to encode all the other information, but not our predefined concept. So the simple way is we will feed its embedding to a downstream linear classifier, and we can extract the concept output. And ideally, if it does not encode any information of the concept, then the downstream linear classifier should predict uniformly. Yeah, that means that the linear classifier does not receive any concept information. So to achieve this, we try to maximize the entropy of the classifier prediction. So the objective of this unsupervised layer is to maximize the entropy, to make the prediction as uniform as possible. And the goal of the downstream linear classifier is to receive the unsupervised input and try its best to predict the correct concept based on the very little information still encoded in unsupervised layer. So this is just a simple minimizing the cross entropy loss. So with these two adversarial objectives, the unsupervised layer is trying to forget all the information related to the concept, and the linear classifier is trying to identify based on the identify the concept based on the remaining information. And we set a higher learning rate for the unsupervised layer to make sure that it can break the downstream classifier ultimately. And we found that when we add this adversarial training objective, it can significantly enhance the controllability of the model. So I will show it later. Okay, so this is all the training design of the CB-LLMs for the text generation. Let me now introduce the evaluation. So the first evaluation is the concept prediction. So this step is just to check is the neuron, the interpretable neurons, encode the correct concept or not. So in this case, we compare with a fine-tuned black box model. Yeah, sorry. In this case, we compare to a fine-tuned black box model that also predict a concept, and we show that CB-LLM's neural activated correctly, so it achieves similar accuracy as the black box classifier. Yeah, another more important thing is the controllability, or we call the stability of the model. So in this case, we evaluate when we change the neuron activations, does the generation change accordingly? That means if we activate like the sport neuron, then the model generation should be related to sports. So when we raise the activation of some concepts, then the model should generate something that is related to that concept. And we can see that for the black box model, there's no stability because the neuron is not interpretable. So changing the neuron activation will have no effect. And the light blue bar here is the CB-LLM designed without the module 2, without the adversarial training that we just discussed. And we can see that there is a lower scalability compared to the full design of the concept bottleneck learning model. So this further proof that the one-to-one mapping between the neuron and concept is very important in building a CBM model. The third evaluation is generation fluency. So this question asks, does the CB-LLM generation quality comparable to the black box large language model? This is evaluated by the generation capacity. So we test the fluency of the model's generation. And we can see that CB-LLMs achieve a similar generation quality compared to the black box model. Okay, and then this will be the last part of my presentation. I will briefly give some use case of how to use the concept bottleneck large model, and share at least 3 use cases: the concept model learning, control generation, and AI safety. So for concept on learning, this can be applied to the test classification case. So assume we have some classification test, then we can manually learn some subjective or bias features in the concept bottleneck layer, and then manually remove it after the training. So this can ensure that the concept does not affect the prediction anymore by, say, setting this concept neuron activation to 0. Like you can see that if we set the overpriced neuron here to 0, then the prediction of this test example will shift from negative to positive. Yeah, this is because, like, if we look into this test example, the customer is complaining about the price is high. Yeah, but also talk about that food is great. So in this case, if we don't want certain concept to be considered in the final prediction, like in this case, if we don't care about the price is high or not, then we can manually remove these neurons, and then the model will not do its prediction depends on this subjective or bias feature. The second use case is the control generation. So here we build an CB-LLM for the news generation. So with a similar architecture, the CB-LLM here can generate the news. If we do nothing, it will just output random news. And we can activate different concept neurons to change the news it generates. Like if we activate the word conflict neuron, then the model generate news will be correspond to word conflict. And similarly, if we activate the sport neuron, then the model will generate the sport news. So this enables us to have like the full control of the topic of what the model will generate. And the final use case is AI safety. So similarly, we can also learn CB-LLMs that with the interpretable neurons that encode an input is harmful or not, and the output is harmful or not. So here we have 4 neurons: the harmful detection, benign detection, harmful generation, and benign generation neuron. So in this case, if we input a harmful query, we can see that the red part, it means that the harmful detection neuron is activated on this token. So if we see the harmful detection neuron is activated, we know that this sentence is harmful. And using this signal, we can activate the benign generation neuron to make the model generation benign. And then we also can do like in the opposite way, then the model will generate something toxic. Yeah, but this is just for showing that we can control the LLM generation. Okay, so this will be everything about the use case. And let me give a summary of the presentation. So our concept bottleneck larger model have several contributions. The first contribution is the strong scalability. Like it can generate the concept labels in no times, and then it scale to larger data and also larger concepts. And it has high performance. So compared to all the previous works, we have the comparable performance to the non-interpretable model. And most importantly, it supports the tracking. Like it's the first work that scale to the larger model, and it will be the first interpretable chatbot. Okay, so this is everything about today's talk. Thanks everyone for listening. Please let me know if you have any question or not.
Thank you. Thank you for your presentation, Chung.
Yeah, thank you so much.
Are there any questions?
Yes, I have some.
Please go.
So okay, I had can you please return the slides that has the steps?
Sure. For which part, the generation or classification?
So when you are doing the embedding model.
Embedding model, I see. It should be here. Yeah.
I can't. Can you? We can't see your screen.
Can you see the screen now?
No. Okay, maybe I can just ask. So basically, my understanding is you take a piece of text and then you embed it using an embedding model, and then you embed the concept, and then you get a cosine similarity score between them.
Yeah.
And then basically you use that as the concept labels.
Yeah.
And then when you using it in your model for classification or for generation, what you do is you learn that the concept score, right?
Yeah. We directly learn it's actually not learning the concept score. We compare the similarity between the activation and the concept score. So there are some freedoms, but they should activate it like in a similar pattern.
Sure, but like when you're like the CBM has a loss, right? So the loss is basically the concept score you got from the similarity, right? That's kind of like the gold, like the ground truth that you're trying to learn.
Yeah, for classification, there are basically two laws because we have a bottleneck, right? So we need to supervise the bottleneck. And also another loss is the their final prediction.
Okay, so for the bottleneck, it's the ground truth would be the output of this embedding model, right?
Yeah,
okay. Correct. So in the generation case, you're doing generation one sentence at a time, one token at a time, because it's a GPT model, correct?
Right.
Okay. And in that case, when you are doing, so you're supposed to be generating the next token.
Yeah.
And then how are you getting like when you're training this embedding model, you are training versus on an entire sentence, right?
Yeah.
So but you're generating one token at a time.
Yeah.
So that means that like how do you when you're training the CBM, how do you train it so that like, okay, now there is only one, like so for example, the cat sat on the hat, so the first thing is so then basically you get the concept for that's the ground truth. The second time is the cat, right? Is that how you do it?
So here our concept is more of a high level concept. So you can label each token with different concept, but that will be kind of noisy and hard to train. So in this work, we only show like we can have more high level concept. Like here, if the sport concept is activated, it means the whole sentence is the whole generation is talk about sport related. So we does not supervise every token when we train the CBL. So like in a training example, if this whole paragraph is talking about sports, then every token here will be labeled as sports. Does this answer your question?
Okay, so yeah, so you basically when you supervise it, you said every token in the sentence has the concept in the sense.
Yeah, although it might be something like the or is, there might be some word that is not directly related, but we only care about the whole sentence, so the whole sentence will have the same label in our case. Yeah.
Okay, and so you fine-tune a language model, correct, to have this?
Right.
Okay. So, and how many examples did you need to get this to work?
It depends on how many concepts you have. So in the classification and generation case, it will be different. So for generation, you will usually need more examples because we also learn the final prediction, right? It depends on how many parameters you likely to train. Like you can assume an already good pre-trained larger model, then we probably only need to fine-tune the unsupervised there and then the also concept bottleneck there. But if you train the whole model from scratch, then it's a different story that you need a lot of data. Yeah, in this case, we assume we have a good pre-trained model. So usually we only need like a few thousand examples is enough.
Okay. So for the steerability test, how do you measure the accuracy here?
Yeah, for the steerability, yeah. Is now the screen showing or not?
No.
Okay. And yeah, anyway, I would already talk about it. So for the steerability, we change the neuron activation, right? And then we want the model output to change correspondingly. So this will be judged by another model like ChatGPT. Like if we change the neuron, if we activate a sport neuron, then we will.
Sorry, you got disconnected.
Yeah, if we. Yeah, so if we so we are talking about the stability. So if we activate the sport neuron, then the corresponding generation we will allow ChatGPT to check if it is sport related. Yeah, if it is success, then it counts as 1. If not, then it's 0. Then we can calculate the accuracy here. Is that correct?
Yeah, that's the answer. So when you activate a sport neuron, so when you had your figure, it was like the CBM, and then there was a ReLU, and then there was an LM head, right? So when you activate the sport neuron, like, how much do you activate it?
Yeah, it's more of like a heuristic base. So if you activate too much, then it can hurt the something to hurt the generation. If you activate too few, then it will have no effect on the output. So what we found, the best region will be around like 50 to 100. It's actually high. Like you need to steer it like with 50 to 100 range of the volume. Then it will start to take effect and have high stability, but also have good generation quality.
And your layer, your CBM layer, is it like in the middle layer, or is it right before the LM head?
It is right before the LM head because we want the full interpretability. Like we want the concept, we want the final prediction to be a linear combination of the concepts. So it is right before the LM head without nonlinear transform.
Okay, so, and basically let's say you're activating sports, but you're generating one token at a time, so you keep the sport activated throughout the process?
Yeah, you will need to we need to keep the activation high. If you shift the concept, because this is not in our training data, we only have one concept correspond to one sentence. So if you shift the concept, you will activate another concept in the middle, then usually it will just have no effect.
Okay. Thank you so much. Very cool work. Thank you.
Yeah. Thanks everyone for listening.
Any other question? Otherwise, I have a couple.
Okay.
So the first question is about the classification module. Can you go back to
classification?
Yeah.
Is a slide now not showing?
You are showing text generation. At least this is what I see.
Yeah, but you can see the.
I can see your screen. Yeah.
Okay, then it's good.
I can't. Is it just me? Maybe it's just me. I'm not sure if people online can.
I can see it, and I'm recording it, so hopefully. Giovanni, can you see the screen?
Yeah, I can see the slides.
Okay. Yeah, you can reload if you want.
Maybe on a side, yeah.
Okay. So
is it?
Yeah, I can see it. I'm just waiting for Aya to come back. Can you see it now? Okay, good. So I have a question here. So if I understood correctly, you are supervising the first block of the model, so the pre-trained language model and the concept bottleneck layer with scores that you are generating by just applying a cosine similarity between the input example and the generated concept texts chunks, right?
Yeah.
So have you tried to measure the difference in accuracy, in the prediction accuracy between using the pre-trained language model, the concept bottleneck layer, and the linear layer on top, against using just the concept scores generated by the cosine similarity, and then using these scores as input to the same linear layer that you trained with the pipeline that you have on the bottom?
Yeah, there are different designs here. What we do here is we does not freeze the pre-trained language model, so the gradient can still go through the pre-trained part. And also another thing you need to consider is, do we train the step 4 and step 5 jointly or separately?
Mm-hmm.
So here we train it separately. We first train the CB-L, and then everything finished, the CB-L is fixed. Everything before CB-L is fixed, and then we train a final linear predictor.
I see. Okay.
Yeah, so this will be more interpretable, because if you jointly training, then they can kind of collude with each other, and then usually the concept here can encode more information.
I see. Okay, I see. So it's sort of like an independent, like a sequential training of this architecture.
Yeah, it's a sequential training.
But you haven't compared the accuracy in predicting the final task using the scores generated by the cosine similarity compared to the scores that you generate with the pre-trained language model and the concept bottleneck layer frozen. The reason I'm asking is that I would imagine that if this baseline, so computing the final prediction using just the concept score generated with cosine similarity and the concept correction as well, is similar, then then I'm wondering, you're using a lot of computation in the first part to get basically to a set of activations that you can obtain much faster using just the cosine similarity.
Yeah.
I would imagine that there should be a gap in performance. I'm wondering how big that is. And, and like I'm wondering, like, if there is a gap in performance, I'm wondering, is this gap due to uninterpretable factors?
I see. Yeah, I probably understand what you are saying about, like, you want to directly use the step 3 label and train a linear layer. Is that correct?
Sort of, yeah. You can actually use the same linear layer that you have on the bottom, like, to be as fair as possible.
Yeah. So the question is why we do like the training later. It is most because we want it to be an end-to-end model. So we are building an interpretable model. So if you directly do step 1, step 2, and step 3, and then step 5, it is also an interpretable architecture, actually.
Yeah.
And then in this case, you probably don't need a training. Yeah, but now we want to kind of build an interpretable model. So we want the model to learn to be interpretable. So that's why we do the further training, and we want the model to be end-to-end. And ideally, they should have similar performance, because what I see here is the neural activation, it learns pretty well. It can actually make a very similar prediction to the concept labels we have. So the performance should be similar, because we also compare to the Babos classifier, right?
Mm-hmm.
Yeah. So the goal here is we want to kind of embed all these things into a language model. So it should be an end-to-end language model. It's not like we design some interpretable pipeline.
I know. I
understand. We want to make everything. Yeah. So this is the main reason.
I'm not saying like that what you've done in the bottom is not useful. I'm just saying, I'm just asking the question because I guess that this, like, using step 1, 2, and 3, and 5 could be just a baseline to compare with.
Yeah, I understand. But like we do not really test this. I assume they should have similar performance. Yeah, because as you can see, our model compared to Black Box model is similar. So I would assume like it will be similar. Yeah, in this case, but I haven't tried that.
Can I ask, how many concepts did you have when you were doing this model?
For classification case, it depends on the data set. Like the largest concept that we have is around like I think it's 500 concepts, and it will be a 14 task prediction.
So for generation.
For generation, it is much smaller, because this is a current limitation, because generation case is much harder to train, and currently we can only have maybe I remember it's around like 10 to 20. Like the largest concept that we have is below 20, because all these neurons are high level concepts, so we cannot have very fine grained concept. But I remember there's another like follow up work from maybe industry, and there's another paper that they try to make it in a fine grained large range model concept. Yeah.
Thank you.
Thank you.
Thank you so much.
All right. If you don't have any other questions, then we can thank you again, Chung-En.
And thank you for inviting me.
Yeah. And see you all next week.